So what I would like you to do real quick is just a review of where we started the last section. So exercise 1 is yours at the very top. All it involves is making a graph of 2 to the x. It's the very first graph we did in the last section. Once you've done that, you can go ahead and pause and we'll walk through the next exercise together. And after you've done with the graph, if right underneath this or to the side right here, go ahead and rewrite what the domain and the range of 2 to the x power is. All right, so if you looked at your notes from the last section, this problem is just strictly review, because it becomes a good transition example for us. So you can look at your table, or maybe you reproduce the points. That's my hope, that you get to that place where you're able to do that fairly quickly. So when I put in 3, 2 to the third is 8. When I put in 2, 2 to the second is 4. When I put in 1, 2 to the first is 2. When I put in 0, 2 to the 0 is 1. When I put in -1, 2 to the -1 is a half. And last but not least, when I put in -2, 2 to the -2 is a fourth. And so here is my graph, my increasing function, my one-to-one exponential function. The domain and the range of this graph, the domain, how far left and right does it go? Well, it goes from -infinity to infinity, meaning I can plug in any x value at all into the exponential. There's absolutely no limitation. The range is a little bit different. It keeps getting closer and closer to the x-axis, like we've already mentioned, but it never goes through. So 0 is a boundary, but it never equals 0. So I use a parenthesis at that point, and then infinity. It clearly goes up. So hopefully, if you have a question, I'm hoping by now you would have asked it, that there's nothing new there. Now, what we're going to do, if you remember, end of last week, we talked about this idea of the inverse of a function. Okay, one of the first characteristics of the exponential I gave you last section when we graphed it, I said, oh, look, it's a one-to-one function. Coincidence, coincidence. So what we're going to do is we're going to step through exercise 2. So firstly, what I would like you to do is the first part. This is very similar to exercises we did in the first section. Use the points of that graph to graph the inverse. Remember, what is the inverse? How do I get the inverse? What do? You swap the x and the y. That is it. Absolutely no thinking involved. You've just got to swap the x and the y values. So please do that. as you're doing that, if you have time and you want to answer the two questions that follow of what is the domain of this inverse and what is the range of this inverse, you probably know the answer to that, but hopefully the graph you just made correlates to that answer. Okay, so doing the inverse, all we do is flip flop the X and the Y values. That is absolutely it. So this, I'm just going to work from the right end of the graph and work to the left. This point on the right is the point 3, 8. So when I flip the X and the Y, it becomes 8, 3. So 8, 3 right here. This one is 2, 4. When I flip the values, it becomes 4, 2. This is 1, 2. So when I flip the values, it becomes 2, 1. This is 0, 1. So when I flip the values, 1, 0. Here we've got -1.5. So it becomes a half and -1. And if you did or didn't do this one, I know it's such a small point, but -2 1/4. So it becomes a fourth and -2. So really close right there. So this is my graph. This is the inverse. One thing to notice, I mentioned this last time about a graph and its inverse. You don't have to draw this. I'm just putting this in here. Remember, a graph and its inverse are symmetric about the line y equals x. It should be the exact same thing on both sides. And you can see, I'm just going to do this as a nice little dotted line in pencil. You can see that both of those graphs, if I folded my Cartesian plane along the line y equals x right here, that it's the same thing. It matches up perfectly. So that's good. That's what we expect. Now, we could have answered these questions without doing the graph because you told me the inverse is just flip-flopping the x's and the y's. So what's the domain of the inverse? Perfect, 0 to infinity. I heard several of you say, because the domain, the x values, becomes the y values of the original function. What that tells me is that the x value 0 becomes an asymptote. So this is I'm a terrible drawer, but this is a vertical asymptote of this graph, the inverse. What's the range of the inverse? Yeah, the y values you can see from our red graph go down to -infinity, and then very slowly they will go up to +infinity. So we're building familiarity. We talked about the exponential graph, and now we have graphed its inverse because it's 1 to 1. So now next thing I'm going to do is just what we're just stepping through the same things we did when we first started talking about the inverse. In example 1, I'm going to walk along with you here, and we're going to find the inverse of f of x equals 2 to the x power analytically. Okay, so what I want to do is I want to know what is the function that describes this red graph. Okay, we've not seen anything like this. Okay, well, that's a great question. So here we go. So who can remind me, what's the first step when I ask you, and I'm going to ask you on the test that we have. Okay, rest assured. What is the first step when I ask you to find the inverse analytically? Yes, the first one is just notation. First step is instead of f of x, I'm going to write y equals 2 to the x. Okay, great. Step 1. What's step 2 of finding the inverse analytically? You switch the x and the y. Actually, this is the inverse I told you. So I'm just going to switch the positions of the x and the y. So instead of a y over here on the left, I'm going to make that an x. Instead of an x on the right, it's going to be 2 to the y power. Excellent. Remember, this is the inverse. We can all celebrate. Ooh, so I'll put some exclamation points. Okay, this is the inverse. But here's the unfortunate thing. That doesn't really help me do much because the y is now up in the power. So now what I have to do is I have to solve for y. Now this is where we have a problem, Because how do you solve for y? We don't have any tools at our disposal to get exponents out of the exponent. So this is where we come across a definition. Okay, so we're going to come back to this step right here. Okay, I'm going to just call a pause for a minute. Okay, and we're going to go down here. We're going to define a brand new function, something that if you take pre-calculus, you are going to see in an inordinate amount of time. We are going to define something called the logarithm. So what the logarithm is, for all positive numbers a, the reason that's positive is the reason why we saw in the last section. A is our base. We're not considering negative bases of our exponential in this class. We're only considering positive bases. And we're also not considering the base of 1 because it's not super interesting. So this is just a definition, and we are going to spend the rest of our time today. We're going to finish out our last 15 minutes just getting used to this definition. And when we come back next time, we're going to do some problems involving this definition. So here's the definition, that this x is equal to, instead of using 2 like I have right here, instead of using 2, I'm just going to have, I'll just leave it right here so we can see both. I'm going to say x is equal to a to the y power. This is my exponential. Well, this is the exact same thing, so I'm going to do an arrow with an equal sign between it. That means exactly the same thing to this. This is the definition. I know this is funky, okay, and I know that we're going to have to learn this, so bear with me. The definition is this: y is equal to logarithm, which we abbreviate log for the logarithm. The base of the logarithm, I use a little subscript, so base a of x. So the one thing I just want you to note here, because when I first learned this long ago, I understand this is wild and weird stuff. So the way I remember this is I always remember that what the logarithm is equal to is the power of the exponential. Notice the y was in the power. When I write the logarithm, I take the power and it becomes the full left-hand side. It is the y value. So now, according to this definition, looking back up when we were finding the inverse, now I can rewrite this without the y being in the power. So according to the definition, this equation here becomes y equals log. What's the base? Exactly, a is right, and in this case, a is 2. Okay. Notice the terminology is the same. It's log base 2. That the 2 is the base of the exponential. It's the same word, and of x. That is my inverse. And the last step in finding the inverse analytically is notational. F negative 1 of x is equal to log base 2 of x. This is my new function. So if you have another piece of paper and you want to write the definition, so I don't have to keep flipping and make everybody dizzy who's watching the video, the next series of problems, all we're going to do is we're going to take exponential statements, write them as logarithms, and then we're going to reverse the process and take logarithms and write them as exponentials. So these problems are just designed for us to get used to this definition. So flipping the page, I'm going to do the first example. 5 to the third equals 125. That is a true statement. There's nothing mysterious about it. We're just going to write it as a logarithm. So, okay, here we go. The logarithm. Help me out. What's the base of my logarithm going to be? 5. It's the same as the base of the exponential. Now, the way I like to do this is I like to do the things that I can grab onto. I can grab onto the base. I can grab onto the power. So what's the logarithm going to be equal to? 3. And then the only thing, the odd man out here is it's log base 5 of whatever this is. So log base 5 of 125. So once you get used to logarithms, which is a process, I totally understand, okay, it's awkward, but once you begin to understand what you're looking at here, this is communicating to you the same information as this exponential statement. It's It's just put in different places. Log base 5 of 125 is equal to 3. So exercise 3, I'm going to give you 30 seconds. Rewrite 2 to the 6th equals 64 as a logarithmic statement. All right, so I got my logarithm, log. What's the base? 2, so subscript here, just a small 2. What am I taking the logarithm of? I'm sorry, what'd you say? 64, yes, and the way I keep that straight in my head is I remember, okay, the logarithm is always equal to the power, so my power over here is 6, so that means what I'm taking the logarithm of has to be 64. Do the next one just so that we don't get used to having numbers that we know. This next one says, okay, if the statement m to the n power is equal to t, write that as a logarithm. Yes, yes, that's a great question. Those 64, the base is normal size because that's what you're taking the logarithm of. That's what the function is applying to. The 2 or the 5, whatever the base is written as a subscript. Just like in our exponential statement, the 2 and the 64 are normal size and the exponent is written smaller. Okay, so it's very analogous. Great question. All right, so exercise 4, I've got my logarithm here, log. What's the base of this logarithm? M. And then what am I taking the base of, and what is this equal to? Okay, it's equal to n because n is the power. And so that means the only thing left, I know what my base is because it's called the same thing. I know what my power is because the logarithm is always equal to power. Okay, that's the most handy thing you can be repeating to yourself. The logarithm equals a power. And so that means what I'm taking the base of is t. So for our last 3 problems today, we are just going to now convert these logarithmic statements into exponential statements. So it's just the reverse process. So log base 6 of 36 is equal to 2. So according to my definition, again, that all this is using the definition. It's nothing else. What's the base of this? What's the base of my statement going to be? 6. What's the power going to be? 2, because the logarithm always equals the power, so this has to be the power. And so 6 to the 2 equals the other number, 36, which we expected because we understand the numbers. So do exercise 5, please. In exercise 5, what is the base of that statement? 7. What is the exponent? 0. Yes, and so then 7 to the 0 has to equal the other number, which is 1, which we expected. So the last problem for the day is convert this logarithmic statement in exercise 6 into an exponential. All right, what's the base of that statement right there? B. What's the exponent? Logarithm is always equal to power, so it's t, that's right. So b to the t, according to this statement, has to equal r. So when you do your homework on My Math Lab, You can do all of section 6.2. We talked about that today. In section 6.3, you can do anything now at the very beginning, the first few problems that are converting between logarithm and exponential. When we come back on Wednesday, we're going to start with example 4. Now, these next 4 examples continue. They are just using the definition. So our first step in solving any of these equations is going to be to write this logarithmic statement as an exponential and then going from there. Okay, because we really don't know how to work with the logarithm yet.